Your building has water in the tank. The gauge said 30% 20 minutes ago. Now the shower runs dry. That is not a supply failure. It is a pressure equilibrium failure. Static head is the pressure generated by the weight of the water column above the pump. Dynamic losses are what friction, valve restrictions, and undersized risers subtract from that head before water reaches your tap. A booster pump is selected against a head curve, a performance graph defining the pressure it sustains at a given flow. When balancing valves are miscalibrated, or when the system was sized for an occupancy it outgrew, the operating point drifts off that curve. Pressure at the control sensor drops. The pump reads low pressure. It trips. Tank still at 30%. Pressure-reducing valves compound this. Set too conservatively on high-zone risers, they shave head below the sensor threshold required to confirm supply. The controller shuts the booster. The thermodynamics are unambiguous. The pump did not stop because water was absent. It stopped because pressure, which the control logic uses as a proxy for supply, fell below a number set at commissioning and never revisited. Drop a comment with your floor number if this has happened in your building. Subscribe now, because the diagnostic sequence starts here. The gap between no water and no pressure to deliver existing water is the core engineering problem. Own that distinction, and you have already outdiagnosed everyone on your floor. The pump does not decide when to stop. A PLC or relay bank does, operating on a pressure band with hysteresis, a dead zone preventing short cycling. If set points were tuned during low occupancy commissioning and the building now runs full, the band is wrong. The controller cuts the pump before the tank empties because pressure drops into the dead zone at peak draw. Poorly tuned PID loops accelerate this. An overtuned gain causes overreaction to momentary transients. 3 toilets flushing, a washing machine filling, pump trips, log records a low pressure event, tank at 25%, software cutoffs leave logs. Pull your relay trip history and map timestamps against peak usage windows. If trips cluster at 7:15 a.m. and 11:30 p.m., that is a control band problem. The people who prepare in silence already pulled that log before it became a crisis. I was in a building where this ran for 2 weeks before anyone admitted the real cause. A single centralized controller monitored the secondary header. A slow leak in a third-floor bypass was bleeding pressure quietly. The controller saw the drop and halted the booster train. Floors 10 through 18 lost service. Tanks retained water throughout. That is cost-driven centralization. One controller, one reference point, one fault mode that disables the network. Distributed designs use zone-level sensors with independent trip logic, so a single riser fault cannot propagate. They cost more. Developers do not install them. Stay rational about what that means for you. You depend on a single controller interpreting a single sensor correctly. When it loses reference through drift, cable fault, or undocumented firmware behavior, it halts supply regardless of tank level. Drop a like if the only answer you received was, "We are looking into it." Before centralized controllers, buildings relied on mechanical float valves and analog pressure switches as last resort backup logic. A float rises with tank level and breaks or closes a circuit. A pressure switch responds to membrane deflection against a calibrated spring. No firmware, no PID. Their failure modes differ from electronic drift. A float valve corrodes at the pivot or scales on the body, sticks open and the tank overfills, or sticks closed and the tank never refills. A pressure switch fouls at the sensing port with sediment and reads false at any actual pressure. Physical states, inspectable with a multimeter. Hardened and ready means knowing where those float valves are, when serviced last, and what a stuck-closed failure looks like on the panel. If that information does not exist on a sheet you can access, the backup is compromised before you need it. Checklist in the description. Watch for air ingress. Entrained air changes effective fluid density. The pump was sized for water at standard specific gravity. When suction lines introduce air pockets, cracked fitting, drain-back design, failed foot valve, the pump encounters a compressible mixture. Flow drops, pressure fluctuates, controller trips. The signature is intermittent. System fails. recovers briefly as air purges, fails again. Residents report water that comes and goes. Management diagnoses demand. The actual origin is suction side air. A check valve allowing line drain back introduces a column the pump must displace before pressure builds, and often trips before it can. Mechanically distinct from blockage. A blocked line gives consistent low or zero flow. Air ingress gives erratic flow with pressure swings. Suction fault isolation protocol is in the description. A grid down event hitting this failure with no stored water is the exact scenario we document to prevent. I have heard that sound. High-pitched grinding from the booster room attributed to bearing wear. What was happening was cavitation, vapor bubbles forming at the pump inlet because available NPSH dropped below the impeller's requirement, then collapsing violently as pressure recovered downstream. Low NPSH is structural. A suction line drawing from a tank at near pump elevation cannot maintain the inlet pressure margin the impeller needs at design flow. At reduced tank levels, the margin shrinks, bubbles accelerate, and the system trips before the tank is empty. Cavitation is harsher than clogging. A clog degrades flow gradually. Cavitation erodes impeller material and destroys seals within hours. Hear that rattle while pressure drops. Prepare in silence. The next replacement invoice comes from your reserve fund. The system stops not from empty water, not from pump failure, but because a strainer is 60% blocked and the head loss across that obstruction pushed the operating point past the trip threshold. A strainer at 50% obstruction produces 2 to 3 times the head loss of a clean unit. Add riser friction and elevation head, pump trips. Tank at 20%. Construction debris dominates in buildings under 10 years old. Biofilm dominates in buildings over 20. Neither clears itself. Degradation is progressive and misdiagnosed as demand. Electrical trips are abrupt. This choking is slow. Strainer protocol is in the description. Check valves produce 2 failure modes that diagnostic teams conflate. A valve stuck partially open allows reverse flow during pump shutdown, generating a pressure transient the control system reads as supply instability. A valve slam closing on rapid pump stop generates a water hammer spike that trips pressure-sensitive controls or damages instrumentation. Root causes: sediment on the seat prevents full closure, producing leak by. Misalignment causes the disc to bind. Spring fatigue reduces closing force below back pressure requirements. Testing is direct. Close the downstream isolation valve, depressurize the upstream section, and check whether pressure rebuilds from the downstream side. If it does, the valve is passing. For slam closure, mount a gauge on the inlet and record the pump stop transient. Hardened and ready means that test has been run. Transient closure is recoverable with a replacement. A permanent obstruction requires line access. The distinction determines the response. Full test procedure is in the description. The losses that never appear on any meter are the most likely drivers of premature shutoffs. An inter-apartment leak, water migrating through a failed fitting inside a wall cavity, reduces available head in that riser with no trace on consumption records. A bypass circuit from an unauthorized installation draws flow continuously. An illegal connection siphons supply from the main riser before it reaches the booster zone. Each loss reduces effective head at the booster inlet. The pump curve and control band were calibrated for a clean network. Unauthorized modifications introduce losses the controller cannot distinguish from legitimate demand, but that push the operating point past the trip threshold before the tank empties. I found one in my own building. A quarter-turn ball valve on the mechanical floor, left open after a renovation, bleeding pressure from the secondary header. Stay invisible and audit what is in your riser rooms. This class of loss becomes invisible under deferred maintenance until the system fails. Bypass detection protocol is in the description. Your building's pump was engineered for average demand, not peak. That decision, made to cut capital cost, is the reason your shower fails between 6:45 and 8:15 on weekday mornings. When a significant fraction of occupants activates fixtures simultaneously, aggregate draw creates transient low-pressure zones throughout the network. These transients last seconds to minutes. The control sensor sits at a fixed point on the header, and if that location sees the transient, the controller may trip the pump before pressure recovers. Systems engineered for peak demand use variable frequency drives modulating pump speed against real-time flow or demand-based set points for concurrent fixture use. Fixed demand systems use set points calibrated during low occupancy commissioning. Prepare in silence by identifying which type you live in. VFD boosters ramp noticeably during morning peaks. Fixed speed systems sound identical at 6 a.m. and midnight. If yours sounds the same, your peak hour failures are an engineered outcome. VFD retrofit guide is in the description. Inspect the building's relief and safety valves. They open under specific pressure conditions to protect piping from overpressure. The problem, an overactive relief valve does not announce itself as a safety action. To the control system, it registers as a pressure drop. The mechanism, a valve set too close to normal operating pressure, or one with a worn seat allowing leak by below its nominal set point, bleeds pressure continuously or intermittently. The booster sensor detects the loss. It reads low supply. It stops the pump. Tank retains water. Nobody connects the valve to the event. Set point drift is real. Spring-loaded relief valves shift their opening threshold over years of thermal cycling. A valve, commissioned at 120 psi, may activate at 95 after a decade. If your building trips the booster during baseline consumption, not peak draw, not equipment events, and check valves and strainers are confirmed clean, audit the relief valve set points. Safety action versus system malfunction determines whether you leave it alone or call for recalibration. Audit sequence in the description. I want to close on the failure mode you have the least control over because it overrides every hydraulic discussion instantly. Mains power interruption stops the booster, not because the tank is empty, not because any hydraulic component failed, because the booster is electrically driven, and the grid, the centralized protocol every high-rise depends on without local fallback, went down. Soft start failures compound this. A soft start module that missequences on power restoration prevents the pump from restarting even after power returns, leaving the system in manual reset state while residents assume a supply problem. Upstream municipal pressure cuts remove the inlet head feeding the booster's suction. A functioning booster cannot pull water not being pushed from the municipal side. The centralized utility protocol is a single point of failure. It has no distributed fallback for individual buildings. Electrical outages and hydraulic faults are distinct. A hydraulic fault is addressable locally. A grid down event is not addressable with a wrench. What you can address is your stored margin. Know the gravity head from your rooftop tank to your floor. A 40-liter reserve at 8 floors delivers approximately 2.8 psi. Passive fill, not a pressurized shower. Know how long that lasts at minimum daily consumption. Hardened and ready is a calculation already run. Storage sizing, gravity head charts, and the municipal pressure cutoff detection protocol are linked in the description. If this breakdown was useful, share it. The building handles average, you handle the rest.